Now, you saw in the first semester of the class that there are some compounds that are insoluble in water. Some compounds are very slightly soluble in water. An example of that would be silver chloride. So if we take silver chloride solid, drop it in water, most of it stays in the solid phase, but a little bit of it will dissolve and will form an equilibrium between the dissociated chloride minus and silver plus ions and the solid silver chloride. And since this is an equilibrium, we can form an equilibrium constant. And the equilibrium constant is the concentrations of the products over the reactant. Now, this reactant is a solid, and so we don't include it in the equilibrium constant, and so only the aqueous products would be included. And we call this a solubility product, KSP, for solubility product, because since the reactant is a solid, it's not included in the equilibrium constant, so you only have the numerator of the reaction quotient. And so this is a product of two terms, and so we call this a solubility product. So this is the equilibrium constant for the dissolution of silver chloride in water, and its value is very small, 1.8 times 10 to the minus 10th. So only a very small amount of silver plus and chloride minus is formed in water. Now, we can use our techniques of equilibrium that we learned previously in the class, and we can let, say, X be the amount of silver plus that's formed in this reaction. So since there's a 1-to-1 ratio between silver plus and chloride minus would also be X. And so KSP would be equal to X times X, or X squared. So X is just equal to the square root of KSP. So this is a way we can find X, or the amount of silver plus and chloride minus that has dissolved in water. And if we take the square root of KSP, we'll get 1.3 times 10 to the minus 5th for X. Therefore, both silver plus and chloride minus in a solution of silver chloride in water would have a concentration of 1.3 times 10 to the minus 5th molar. So it's a small concentration. Now, this would be for a saturated solution of silver chloride. Let's look at another example. Say we have magnesium hydroxide. This is in the solid phase. And we drop it in water, and it will dissolve slightly. To give magnesium 2 plus and 2 OH minus ions. So now you can use the table that you had in the first semester for molecular ions, and you can use the rules for electron configuration to predict the charge on the magnesium ion when it's formed in water. So if magnesium loses 2 electrons, it will have a noble gas electron configuration, so it'll be 2 plus, and the molecular ion OH has a single negative charge. So having 2 of them will balance the charge in the molecule. So this is the equilibrium expression for the dissolution of magnesium hydroxide in water, and KSP is fairly small. It's 2 times 10 to the minus 13th. So now we use our tools for equilibrium. So we'll let X be the amount of magnesium 2+ that is formed. And since there's a 1:2 ratio between magnesium and hydroxide ion, the amount of hydroxide ion that's formed will be 2X. And therefore the equilibrium constant, solubility product, will be now remember, this OH minus will be squared because that coefficient is an exponent in the equilibrium constant. So that means we'll have X for magnesium and we'll have 2X for hydroxide, but then we have to square that. So this will be 4X cubed. So we can solve for X. So X will be the cube root of KSP divided by 4. KSP has this value, so we'll plug this value in under the radical, and then solving gives 3.7 times 10 to the minus 5th for X. So the equilibrium concentration of magnesium 2+ is X, or 3.7 times 10 to the minus 5th molar, and the equilibrium constant, or the equilibrium concentration of hydroxide ion is 2 times X, so it'd be double this, so that would be 7.4 times 10 to the minus 5th molar. So these are the equilibrium concentrations in a saturated solution of magnesium hydroxide.